Swayam Prabha. Digital India. Educated India.
Okay, thank you. So I am here to present my talk on the importance of field measurements in coastal modeling. So over the period of this course, you would have looked at various aspects of coastal modeling. So it's kind of counterintuitive that I am speaking on the importance of field measurements, which is something that you do at site. And the whole concept of coastal modeling is you can try to eliminate people going to site. So what is this link and why this is important will form the crux of our talk. So as you have known, over the period of this course, you would have understood what a coastal zone is, and it is the region where you have land and sea interacting, and various processes takes place, and you try to model these things. So over here I have presented to you a very typical cross section of a coastal region, and you can see the beach, you can see the waves, you can see a small tidal flat, etc. So each of us would have an interest in this coastal zone. We would like to study, some of us would like to study what happens to the waves in the coastal region. Some of us would like to know what happens to the beach, and some of us would also like to understand what happens when there is an extreme event. So like that, our interests would be varied in this coastal field, but we have to understand it through certain models. So just summing it up, why would we need to study the coastal zone? These can be for research, scientific purposes. It could be because we want to build a structure in this coastal zone, or we just want to protect this coastal zone, we want to do some management of this coastal zone, or we have got some request or requirement from a government agency or somebody who owns that location that they need certain changes to that coastal zone. It could be for military, it could be for defense purposes that we want to develop something, or any coastal infrastructure, port, harbor, or you want to improve the tourism in these. So all these would always want us to study the coastal zone. These are different reasons why we would study the coastal zone. Just to put it out to you, when you walk into a coastal zone, what all could you visually see? So you can probably see the beach, you can see sand. In some places you find rocks, some places you find sand, you would find vegetation, you would see that areas where the water has run up and it is wet and some part is dry. You see some small backwaters getting formed. So similarly, there are different things you generally visually observe. So any field studies basically starts with this, what you observe. So when you can observe waves, you can observe tides, if regions which have very large tidal variations, if you go there, one point of time there will be water and another part of the day it will be totally dry. Similarly, you can feel the wind, you will feel that wind is blowing in one direction in the morning, it's blowing in the other direction. Similarly, the sediment itself would be varying in different parts. You could see some scouring happening. If there was some broken bridge or something, you can see under it that some scour has happened. You also see that humans have intervened, they have built some structures, groins, breakwaters, etc. So all these you can visually see. So this is your basis of field measurements. What you see, you want to measure. So one step from being a visual stimulus to measuring it is what is field studies is all about. So from visual we move into measurements. So for measurements we can measure the wind. We have anemometers which we can place, we can understand wind speeds. We have waves, we can check how much wave heights we are getting, we can measure. We can measure currents, you know, any difference causes currents, so we can measure currents. We can measure tides. What we have seen, we can actually enumerate it with numbers that, you know, the tide rises this much. We can also measure the water quality, which is a very important factor when we are talking about utilizing that coastal zone for some particular purpose, for withdrawing water or letting off influence. We can also study the seabed, what is the type, we can collect samples. Similarly, we can also measure the shoreline profiles, how the shoreline is going. So, all these from visual, we have moved one step further to make ways of measuring these things. Now, there is going to be an obvious question to modelers that, hey, now that I have got computer models, what is the whole point of going to the site and measuring or even observing? I can just do everything in the computer model. That is a very basic question that people will get in their mind who don't know about the subject, who are just looking at it from outside. You are the experts, so but somebody from outside will come and say, you have all the models with you, so what is the big reason that you are asking also for some measurements? See, one of the main reasons why we tend to always go back to field measurements is that most of these things are very random in nature. The wind, the wave, the current, and all the causative factors, they are not like clockwork. You cannot just stand and say that this is what will happen to eternity. We are not able to give that assurance. So that means what you model might not always be what you want to get at the field. And even the models, when you do a deep dive into understanding each of these models, you would find that most of them are very simplified versions of your physical phenomenon. In fact, even most of your equations, everything are based on very simple assumptions, the small amplitude wave theory, or even any model, when you break it down into the subgroups, what is it doing? It's a very simplified version of the real physical phenomenon. And many of them would, to your surprise, would be empirical in nature. See, when you are formulating a model and when you want it to move from one time step to another time step, you cannot allow it to keep thinking forever, so it has to quickly move from one time step to another time step. So when the physics is very difficult, so what you do is you kind of tend to take up some empirical values. So there will be a lot of empirical nature in the model when you deep dive into it. Similarly, these models might also require some calibration. So the physics might have been set based on certain observations in a particular location, and they would have given you the model. But now, how do you make sure that in a particular location, whatever has been calibrated before is working? So you need to do an initial calibration. And then at times, if you are a model developer yourself, you might have to keep benchmarking your model results with what is happening in the field to get the confidence. Similarly, it's very difficult sometimes, we don't have sufficient accurate field data. So that is why we have to go back and check whether what our model does is right. So now that I have told you that there is so much of difficulty with these models and fieldwork is important, the next obvious question is, sir, can we just drop all these models? Why don't we just do the field analysis only? We will collect data in the field all the time. Why all these models? So there again we have challenges. One, we cannot control the environmental conditions. So what we see today might not be there tomorrow. We will not be able to recreate a scenario that we want to model. It's very expensive. It is difficult to get manpower, time consuming, and there is no guarantee that the data you collect also would be to your requirement. It might be random. And of course, very difficult to do it in extreme weather. So one of the most important things we want to study is what happens during extreme weather. And actual data collection during extreme weather is very rare and very difficult. Similarly, some locations it might not be convenient. There are remote islands, there are difficult to access places, so where we have to kind of do modeling studies. Similarly, it is also difficult to cover all regions and places. So tomorrow if the government wants to formulate a policy for all the coastal states, we cannot say that give me 10 years, let me go study all the coastal states. By the time we start and finish, the first location would have already undergone significant changes. So when we want to do in a large scale, when we want to understand a wider area, we have to switch to modeling. Of course, difficult to do at site. In the Indian context, if you carry a RTK or if you carry a survey equipment and walk down the coast, be guaranteed that the villagers will come and surround you. It's not easy to do any studies, so that physical difficulty is also there. there have been lot of studies, field studies that have been mounted with the pure aim of developing models or understanding certain physical interactions of wind wave, etc. So I have just given you a few examples. So these are field works that are not done for any purpose but purely to understand a particular concept. So those sort of work we still are trying to mount in our Indian context, but there are lot of studies that go out doing a particular set of field measurements. They have very good you can say terms of reference as to what they are collecting. So that is why if you see these studies done at Duck Point in 1987, but still that data set is used whenever you are talking with one line models, longshore sediment transport, you still go back to those data sets. Similarly, the John Schwab field data collections, anybody who is working in wind wave interactions, they would still refer to that data set. So when you set out a clear terms of reference, when you collect very robust data where you make sure that everything is calibrated, everything is captured clearly and documented, then your data set becomes very important and lot of people can continue to utilize it long after you have collected the data. So once we have seen the importance of these measurements, where do we use them? You know, what is the purpose of collecting these waves, currents, tides? It simply cannot be research alone. So there should be some practical utility also. So for waves, whenever we are using for design, when we want to check the force, when we want to calibrate models, when we want extreme event forecast, so waves measurements come in over there. So similarly currents, you want to model certain circulations, etc., you use those measurements. Tides, similarly seawater data quality, sediment quality. So many of you who would be working in certain models that predict beach change, shoreline change and all, you would see that even this sediment particle size, fall velocities, they are very important. So these measurements, when you do it at site, you get the confidence to use the right values. So that is some of these importance of where we use the field measurements. So next we have seen what we visually observe. From visual observation we moved into the fact that we need to measure them. We saw the importance of these measurements. Then the next obvious question is, how do we do it? You know, you are saying measure wave, measure tide, how do we do it? So we have very typical equipments for these, how we can measure waves, how we can measure tides, etc. Here I am just going to simply show you some of the equipment that we have used in our studies, in our consultancy work, etc. This is only to give you an idea. So the next question is this the only equipment? Is there no other equipment? No, I accept that it is not. The idea is to just introduce you to the fact that we can do these measurements. So as you all know, the tides are rising and falling. So this is a simple a tide recorder. We call it the automatic tide recorder. So when you have a location which is safe enough, probably like a wharf or a jetty, and you know the reference height, what it is, then you can deploy this and calibrate it. So every time the water level rises and falls, it is going to give a pressure on the sensor, and that rise and fall is converted into your measurement as meters up and down. So this is a typical installation how you would install. So when you don't have these wharf or jetty, it's a totally new location, there is nothing over there, then you have certain other measurements. You kind of tend to you can see here this particular configuration, it's a mooring configuration to put it in the seabed and then measure the tides. So many times the challenge is not going and installing it, the challenge is to understand how it is installed, where it is installed, for what purpose it is installed, how much tolerance you can expect, what would be the tidal range in that location. So do I put a steel rope for this, or do I put a normal hemp rope for this? All this makes minor differences to your measurements. But for what you are measuring, what purpose you are measuring would determine how much of accuracy you would be looking forward to your data. Similarly, we have different forms of current. I have just tried to briefly capture. So, people who are involved in the studies of longshore sediment movement, etc., they rely on this particular longshore current to establish values of net drift, etc. Similarly, deep water currents would be used when you are doing offshore structures. Similarly, people might be even researching on rip currents. So, all these phenomena also we can measure. We have something called as the current meters. There are different principles in which they operate. You have rotary ones that physically move and measure current. You also have optical ones that send out waves, get reflected due to the currents and measure. So, this is a simple current meter. We can deploy this, and similarly, you might want current at one particular location, you might want it over different layers. So, you have different instruments for that. Similarly, waves, everybody is keen to understand what is the wave climate in a particular region, what sort of waves you can expect in that, because fundamentally your wave height determines a lot of things, like your entire breakwater design, all root finally comes down to what is your wave height that you have assumed for the design. So, waves, there are different ways which we were using waves. Few years back, a few decades back, we were just relying on visual observations. People who go out to sea would just note down what wave heights they have seen. Somebody compiles that, and that becomes your basis of wave data for your entire coast. From there, we moved on. We tried to take up some systematic studies through buoys, etc. Now we have advanced, we have gone with satellite imagery which can measure wave heights. There are, if you just say wave height measurement, there are a spectrum of ways which we can measure waves. But again, what are we looking at when we say waves? Am I looking at standing here, what is that one wave that is coming at me, or am I looking at a large picture? Because people would be looking at waves acting as a global phenomenon. Some of them would be studying for large grids, probably the entire coastal India you want to understand. So, depending on that, you would go for the type of wave data that you can borrow. So, here you can see that your satellite has been picking up wave heights over a very large spectrum. Then you can run models from these large spectrum to a particular location. You can, basically tune your computer and say that this location has been getting this data. Now, come on, get me for one particular location, what is it? So, there are a lot of service providers who do that. And similarly, you can also mount certain high resolution requirement, like you focus on a particular region and try to collect data, like LIDAR and other things. Now, you have a lot of technologies that can focus and get you a small area data. Or if you are interested in a particular location, then you can even deploy buoys. So, now you know about NIOT and NIO, they have their own floating buoys that measure data from particular locations that is used for different purposes. So, this is a typical wave rider buoy. So, when we deploy this floating in the sea, it moves along with the wave and it will be able to measure how much it rises and falls. Similarly, the direction from which the wave is coming. All these data you can store it inside as a like your USB, you have a memory, or it can be transmitted also. Similarly, water quality, when we want to understand, there is a variety of measuring devices. Something very simple, like you want to understand turbidity and you want to understand salinity, you want to understand temperature, you have different probes, you can calibrate them, and when you are measuring in any location, you can deploy them. You get a time series of how the turbidity varies, get a time series of how salinity varies, temperature varies. Again, all of these are inputs to some models somewhere. Okay. So, when I am trying to do an analysis of how an effluent would behave, so these sort of time series gives us some idea how the temperature varies in that location. So, temperature will be a very important parameter in your model when you try to see how the dispersion is taking place. Similarly, we can understand the depths available. We have different equipments to do something called as a bathymetric survey. So these are again working on the Doppler principle. You send a sound wave, you get it back, you measure the time, based on that you get the depth. So how deep your coastal basin is one of the very important requirements even for your model. Many of the models will have some global maps with some global contours, but how accurate they are is questionable, because they are based on very old information, and they are based on a lot of approximations. So when you want to do a particular region's modeling, when you have accurate bathymetric data, the quality of your modeling output also increases. So you can measure depths. These are different makes of the same equipment, and you can typically prepare such contours to understand how the depths vary. So again, different coastal regions will differ. There are coastal regions where the contours vary very uniformly, like every 1 kilometer I move, there will be 2 meter drop in depth. So it's a very nice uniform sloped kind of thing. There are other regions where the contours are all very different, and these all are reflective of the particular coastal region's uniqueness. So can I just go without bathymetry in a model, or should I really insist on doing that bathymetry? That would come to you based on experience. So that is where somebody who's been a modeler, who has been doing models at different locations, he would know that, this particular region, I can go with whatever standard data is there and do the model, I will still get a good output. Oh, this region I cannot do that. I'll give you one typical example. If you are going to do something off the coast of Odisha, you can be almost sure that there might not be major changes, very gentle slope, well defined depths, hardly any human interference through structures or anything. So those regions we can definitely go without a bathymetric survey. We can go for a standard depths and do the modeling. We might end up with good results. But if you switch to this side, the Gujarat Gulf of Kambat coast, you have about 15-20 ports. Each fellow is dredging every day and night. He is dumping different locations. So this fellow himself will not accept what the depth is, what the other guy is saying. So these are very dynamic regions. So add to this the huge tidal changes, you add to this the input from the rivers, those regions are very dynamic. So there, going with standard modules will be very outdated. You might not get the results you intend. Similarly, we can even move one step ahead. We can collect measurements on the sea floor and also the seabed. So though these are not very much used in research or not used in the academic sense, this is very much used in the industry. So I wanted to introduce you to this also. So these kind of give a understanding to people who are going to work in that coastal region what to expect. In marine, whatever you do, if you are able to define what you are able to do, that is where your cost saving comes from. If you go in an undefined manner, your cost escalate exponentially. For example, if you want to call a person to do a dredging in your location, you have to know what the depths are, what depths you want him to dredge to, and what are the type of dredge materials he is going to handle. Now, if you don't know this and you call him, he will come with some assumption, and suddenly there is rock and there is suddenly some sunken boat and all this. Immediately the scope of work changes, and for every day you keep losing money or you will get charged more. So that is why in industry it's always important that they know fully well what they are entering into. So this is a typical side scan multi-beam kind of equipment. What this does is it kind of maps your seabed, and it can tell you whether there are some exposed rocks, is there some sunken objects, etc. Similarly, you can see here some typical records. So once there was a cyclone and you have the trestle broken, where it has fallen down, you can scan and you can find out. So you can basically avoid those regions for your new development. So these sort of studies are very helpful in your planning, you can see buried pipelines. So before you start digging or you start constructing something, you should know what is there, how it is. Always what is there on paper and what is there in the field will be different. It might not go as per plan. You might have said put the pipeline from A to B, but once you take it into the sea, there is no guarantee that it will sit between A to B. It might go anywhere. So these sort of studies help us get a better understanding. Similarly, something called as sub-bottom profilers. People who are well known with geotechnical studies would appreciate that you want to know the entire soil column, how it is. Similarly, you do something like this in the marine also. You understand the marine seabed, but putting a borehole is very expensive. So where to put a borehole? Do I need a borehole first of all? So all these decisions you can make through certain field measurements. So this particular sub-bottom profiler basically understands at what level you are going to expect rock, whether you are going to expect rock at all. So this will give you an idea, okay, this seabed is predominantly based on clay, or this is based on sand, or it's based on silt. So I need to go 30 meter to understand this thing, and let me choose my location. So those sort of critical decisions you can take based on these sort of studies. So this is a typical base for you to understand how much penetration is happening, whether your structure needs to touch that or you need to go further down. So all this would, see, classic example I would give you. Suppose that area had rock in say 3 meters itself. Now you have floated one big tender that he has to put 30 marine boreholes for 30 meter depth. Okay. He will charge you for that. He will come there. By the time he's hit the 3 meters, there is rock, his job is finished. And in 2-3 days, he would finish everything and he will charge you still for the same thing. So this you could have avoided if you have previously known what that sort of location is. Again, this comes not just through field measurements, it also comes through your experience of working in a coast. That is why it is very important for coastal modelers to also go to the field. Very often, whenever you get a chance, go to the site, go to the field, understand what is there. So many of our professors here in IIT and people who have been working, most of the knowledge is through this accumulated experience of being at the site. So when you tell them a location, without resorting to studies, without resorting to anything, they would tell you what you have to do in that location. So that comes when you go out to the field. So this is a typical shallow seismic. Similarly, your sediment size, I was talking to you about this before, how it is important in your models. So these sediments can vary from large boulders to the tiniest of clay. So it might not be uniform, it might be mixed. In fact, how this varies also gives you some idea of how the sediment is drifting, in which seasons do you expect clay. Like a typical example, when we tried to develop a fishing harbor in a particular location, we did all the field studies in the nice calm weather, and all the studies, everything is done. And come winter, when there is large movement of silt and clay, there is a huge deposition of clay in that area. So what happens is, now when the contractor is trying to build something, it is sinking. So there is now a huge mismatch between what we had predicted as amounts for material and what is actually happening at site. So this again puts the importance of understanding at site. You should have taken measurements, you should have understood what happens in different seasons, etc. Again, where these sediments comes from, we should also improve our knowledge to understand why we face issues of siltation, or why we face issues of excessive dredging. So we have some of the very high riverine inputs in our east coast. So that is one reason why in Indian coast it is always a challenge to understand these dynamics. So for some of you who are doing very fundamental research about sediment movement initiation, how the sediment would move, etc., there also classifying these sediment sizes become very important. So this you can see typically when we are doing the field studies, we try to collect grab samples and analyze what it is. If you have put a borehole and taken out, you could even see the layers, how it is changing between different layers. So this is a typical example for you. This particular grab sample we can do very easily. You don't need any sophisticated equipment. But when you do core sampling, you have to do a little more detailed collections. We have these sort of core samplers, different ones which we can do, and then you can layer them out. Sorry. And if you need for a particular depth, like for example you are designing a structure that whose basement you want to understand the fixivity, depth, etc., then you go for the boreholes also. Similarly, there are few more field measurement equipments like magnetometers. These help you to identify between those which have ferrous content and which don't have ferrous content, because when you do the earlier studies you would only get it as a block. So you don't know now whether it is a rock or it's something that vessel that has sunk, or you don't know. So when you try to do a typical magnetometer survey, you understand also the nature of the rock, whether it's a very hard rock or whether it is a man-made structure that is sunken inside. So those measurements also you can get. So this is nothing but it's basically a small radioactive thing that you keep moving in the seabed. Whenever it is close to magnetic objects like ferric objects, the field will get distorted. So you basically are measuring this all the time, and you are able to lay out maps saying that these regions have very high activity. So I am presuming that these will be ferric in nature. So here I have shown you a magnetometer. It's called an anomaly map. So basically what we were trying to do is this trestle had broken, as I had told you, and it had spread to different parts. So now we scanned the area, we found out where it is spread, and then we had to confirm that it is from this thing. It is not something else that is lying over there. So we do this magnetometer and we were able to kind of come to the correct conclusion that whatever is broken here has spread to all these locations. Coming to the most important and also part of my research, this littoral drift and measurements form a very important aspect for people and students who are doing coastal modeling and also research in this area. So now whenever we are talking of coastal modeling, we are invariably trying to understand what is happening to the coast, and the major differentiator for the coast is the movement of this sediment. So it can move along shore and it can move also up and down in a cross shore manner. So we have different models that help us understand this, but we are also more interested in understanding how they have come up with these models. So both are important. So many of them are historically based on certain empirical formulas and certain measurements that they do. So here I have shown you some typical methods used in research for understanding this longshore sediment transport. So you can simply do a beach fill study. Basically you have a known volume excavated, and then you try to understand how fast that it is getting filled up. Or you can collect sediment trap values. You can go and measure physically how much accretion erosion happens between different breakwaters, groins, etc. You can simply observe a natural spit that is forming over years, how much it is growing every year, over decades how much it has grown. Then you have different tracer methods, you have bed traps, you have optical scatter instruments, you have video monitoring and cameras. So these are all different measures to physically verify what is happening in terms of longshore drift. So these are experimental setups that people are doing. See, very often as a modeler, people would say, CERC equation, that is enough. You have completely mastered longshore sediment transport. But if you go into the depths of how the CERC equation came up, it has come up through a very small field study, and whatever they have been able to do empirically, they have created that model. Now the question is, how is this model so successful? See, the model is successful because the scale we are dealing with is very large. Okay. Now, when you are talking about people, in Kumbh Mela, it doesn't matter if 100 people extra or 1,000 people less are there, because lakhs of people have gone. It doesn't make a difference. But suppose you are looking at say very particular numbers, then the scale becomes very important. You cannot say in this class 1,000 people can come. It doesn't work like that. This class means we have capability for 40 people, 50 people. There every number matters. Whereas in Kumbh Mela it doesn't matter, because it's a very large volume we are talking about. There another 100, another 1,000, even another 10,000 doesn't matter. So those models like longshore models, old ones, they are all working in a very large scale. So you can apply it and you can be wrong, but it won't matter in a scale. But as researchers, we would not stop. We would like to continue to improvise better. So that is why these studies still continue. We don't stop at it. So this sediment trap collection at site, I have just taken some old photos. Earlier they were doing that. So you can basically see they are trying to collect the variation of sediment at different profiles and then trying to come out with what would be the flow and how much it would vary, etc. This is actually very old NIO photos I have borrowed. I'll show you mine. So this is a dye dispersion study. So when we are looking at certain locations, we can kind of introduce the dye and see how it varies spatially, what time it takes, etc. These will be then your indirect measurements for understanding longshore sediment movement. Similarly, you can deploy floats, you can observe them. So this is my study which I am trying to do here in Mahabalipuram. So I was trying to do this float study. Then we are trying to measure near shore depths, because certain instruments cannot be deployed in the wave breaking zone. We improvised with some sort of measures to understand that, and we are taking beach profiles, etc. So these LEO measurements are some of the very basic ways of measuring your longshore current and drift. So typical record how to do it. Similarly, cross-shore measurements are also very important. You want to understand how your profile would change after a storm or after high wave activity, what happens, whether that region is safe, what would happen. So those sort of studies also you are doing. So this you can see typically they collect over a period of time. So whether that beach is stable, it would form back, or it is continuously losing, those sort of measurements we have to understand. So this is what the typical bar berm profile. Most of your process based models like S beach, X beach, they all try to recreate this berm and bar profile on it. So this is some measures which they are using abroad to do the same studies. They have these sort of equipments, buggies, etc. they can use to understand. And this is becoming now more common. Coastal snap, camera based, lidar based, all this again helps us to understand what is happening. So when we as coastal modelers are doing certain work, we are always having some benchmarking to compare our models with to understand this. So this is us during COVID. So you can see here the rapid erosion that occurred post high wave activity. This is actually during cyclone Nivar, we were doing some studies in Mahabalipuram. So we were lucky enough to understand all these things. So I have just put it for you. So this is what you would not be able to visualize in a model. So unless you have been to that location, so when sitting in a computer and saying extreme wave, oh it will, this is what will actually happen at site. So it gives you a very human perspective of understanding, because in a model you can always give 2 meter, 2.5, 3 and keep getting your results. But what is that 2 meter wave? That physical impact you will understand. So when you as a modeler, when you write your report, this is what will kind of guide you to write the right values, will guide you to take the study more seriously. Because you are going to be in charge of something that will have such drastic effects on your shoreline. So that is it. Thank you. I tried to complete it very fast because we are already late, and some of you have any doubts, I am open to talk to you. Others, thank you.